Welcome to Comparative Anatomy of Vertebrates. Today, we're going to explore one of the most fascinating structures in biology, the vertebrate skull. We will discover how it is not just a single bone, but a complex fusion of three distinct evolutionary parts. By the end of this lecture, you will understand how ancient fish gills evolved into the jaws we use to speak and eat today. Let us dive in. Now that we know what we are studying, let us start with a simple analogy. Imagine you are building a highly advanced armored vehicle. You wouldn't just pour metal into a single mold. You would need a protective inner capsule for the delicate computer, a mechanical framework for the engine, and an outer armor shell to protect everything. The vertebrate skull is built in the exact same way. It uses three completely different sets of biological building materials that evolved at different times in history. These parts start as entirely separate structures in an embryo, but as the animal matures, they tightly fuse together to form the complex, unified structure we simply call the skull. Building on our vehicle analogy, let us look at the inner protective capsule. This is the neurocranium, also known as the chondrocranium. Why does this specific part matter? Without it, our central nervous system would be completely exposed to catastrophic physical damage. It acts as the primary brain case, forming the deep, ancient foundation of the skull. Specifically, it creates the floor and the sides of the skull cavity, providing a rigid platform that supports not just the brain, but also the delicate sensory capsules for our eyes, ears, and nose. It is the ultimate biological shock absorber for our most vital organ. Moving outward from the brain case, we find the mechanical framework of our vehicle. This is the Splanchnocranium, or visceral skeleton. This structure has a truly incredible evolutionary story. Originally, in ancient jawless fishes, this framework simply supported the gills for breathing. But over millions of years, it evolved and repurposed itself to form the jaws, the hyoid apparatus, and even the tiny bones in our middle ear. This transformation gave vertebrates the dynamic mechanical ability to bite, chew, and eventually hear airborne sounds. It completely changed how animals interact with their environment, turning passive filter feeders into active predators. Finally, we reach the outer armor shell of our biological vehicle. This is the Dermatocranium. In early predator-filled oceans, early vertebrates desperately needed heavy armor to survive, and this structure provided exactly that. It consists of dermal bones that literally form within the skin. Today, it creates the outer casing of the skull, including the roof and the bony palate inside the mouth. More importantly for us, the dermatocranium forms the very structure of our human faces. When you look in a mirror and feel your cheekbones or your forehead, you are touching the evolutionary legacy of this ancient dermal armor. Now that we have defined the three components, let us see exactly how they fit together. In this exploded diagram, you can clearly see the modular design of the skull. Notice the blue structure in the center. This is the neurocranium, forming the deep brain case and housing the optic and nasal sensory capsules. Below it, highlighted in yellow, is the Splanchnocranium. You can see the gill arches and how they transition forward into the jaw bones and hyoid apparatus. Finally, the pink structure represents the Dermatocranium. See how it acts like a helmet, providing the outer roof, the facial bones, and the upper jaw armor that wraps around the entire system. Seeing these parts visually brings us to an important real-world application. Why is it so crucial for modern scientists and doctors to understand this ancient tripartite division? Because this evolutionary history directly impacts human medicine today. When a human embryo develops, these three components still start as entirely separate tissue layers before fusing. Sometimes errors occur during this fusion, leading to congenital facial deformities. Because surgeons understand this modularity, they know exactly which embryonic tissue layer is responsible for a specific defect. This knowledge allows them to perform highly precise reconstructive surgeries, tracing the medical issue back to its exact developmental origin. Beyond medicine, understanding these structures helps us analyze animal behavior, particularly the Splanchnocranium. To truly appreciate its importance, we must look at how it functions mechanically as a jaw. In physics, the jaw acts as a simple lever system. Muscles apply force to a specific point on the bone, which pivots at a joint to create a biting force at the teeth. By simply analyzing the lengths of these jaw bones, we can predict the exact feeding behavior of an animal. We can determine if a skull was built by evolution for a strong, bone-crushing bite or a fast, snapping bite to catch quick prey. This mechanical lever concept leads us directly to a mathematical relationship. We measure the efficiency of this jaw system using a formula called mechanical advantage. Conceptually, this formula compares the input effort to the output result. Let us look at the symbols. MA represents the mechanical advantage, which is a pure dimensionless ratio, indicating the force-multiplying efficiency of the jaw. Lin is the in-lever length, measured as the distance from the jaw joint to where the jaw muscle attaches. Lout is the out-lever length, the distance from the joint to the actual bite point on the teeth. Physically, when the value of Lin increases, the jaw produces a much stronger bite force. Conversely, when Lout increases, the jaw produces a faster bite, but with less force. Before we move on, let us see this formula in action with a concrete example. Imagine a paleontologist discovers the skull of an extinct wolf-like carnivore. We are given that the distance from the jaw joint to the main muscle attachment is 5 centimeters. The distance to the front canine teeth is 15 centimeters. We are asked to calculate the mechanical advantage to understand its hunting style. We choose our formula because it perfectly models the jaw as a lever. We substitute 5 for the in lever and 15 for the out lever. The centimeter units cancel out, giving us 5 divided by 15. This yields a final mechanical advantage of 0.33. Because this value is less than 1, it physically means the jaw is optimized for speed rather than crushing force, perfect for snapping shut on fast-moving prey. Now that we have seen a carnivore, let us compare it to a heavy, plant-eating mammal. This herbivore needs to crush tough roots. We are given a massive muscle attachment further down the jaw, making the in lever 10 centimeters. The bite point is now at the back molars, making the out lever 12 centimeters. We are asked to find the chewing efficiency. Again, we use our mechanical advantage formula. We substitute 10 for the in lever and 12 for the out lever. Notice how these numbers are much closer to each other now. Dividing 10 by 12 gives us a final mechanical advantage of 0.83. Physically, this higher value indicates a massive increase in force transmission. This explains exactly how herbivores generate the immense, sustained crushing forces required to break down tough plant fibers all day long. This brings us to the end of our journey. So, let us review the most important ideas. First, we learned that the vertebrate skull is not a single bone, but a magnificent composite structure born from three distinct evolutionary origins. The neurocranium provides the deep foundation to protect the brain, while the dermatocranium wraps the system in protective dermal armor. Second, the Splanchnocranium offers the dynamic framework for jaws and hearing. Finally, we saw how the jaw acts as a mechanical lever, where calculating the mechanical advantage allows us to predict an animal's diet purely from its bone lengths. You have now covered the full topic of the tripartite skull, seeing exactly how evolution repurposes old structures to create highly complex anatomy.